Some of you may have heard that. So Aaron is going to speak to us about how to hack OAuth. And just to give you a little background about Aaron, he is a senior security architect at Okta and the editor of several specifications for the IETF and W3C, and maintains the OAuth.net. Aaron has spoken at conferences around the world about OAuth, data ownership, and qualified self, and his work has been featured in Wired, Fast Company, and more. And I just found out you just got back from Zurich last night, and he's leaving on a plane tomorrow for Copenhagen? Yeah. So he's a very busy gentleman, and I'm glad that he could be here today to share his information. So please welcome Aaron.
Thanks for the introduction. I'm Aaron Parecki, and yeah, today we're going to talk about how to hack OAuth. I am, like you just heard, I'm a senior security architect at Okta. I'm also heavily involved in standards, so I write standards and contribute to web standards like OAuth. So I have a lot of experience with the nitty-gritty details of these kinds of things. I also run a conference, Indie WebCamp, and that's I was actually just at one last week in Brighton, and that's a conference all about online identity and data ownership, which is encouraging everybody to have their own website and not only rely on Twitter and Facebook for your online identity. So that seems to be getting more and more relevant every day. My website is aaronpk.com, and my Twitter is aaronpk. Please tweet your questions at me during the talk. I can't promise I'll answer all of them during the talk or that we're going to have time for questions at the end, but I will answer all your questions on Twitter afterwards. If Twitter is not your thing, you can also tweet your questions to me on Mastodon. So I assume some of you probably have an account on some Mastodon service. So yeah. I also maintain OAuth.net, which is like the community website of OAuth, and OAuth is been around for a long time, and it's taken it's evolved a lot since it was started. And it's kind of gotten to the point that trying to learn about OAuth and how these things work is like trying to find your way through a maze, because it turns out that it's not even just one spec. It's actually probably like almost 24 at this point. Various specs, some of them are even made in different groups, not even necessarily the OAuth working group, but there's a lot of extensions developed by other groups. And yeah, it can feel like a real challenge trying to understand this space, and when really all you were really trying to do was just build your application at the end. So instead of talking about the specs, I want to start with talking about some background on what OAuth was created to solve, to kind of set the context, and then we'll talk a little bit about how OAuth works so that we can see where we can go and actually try to attack it. Does anybody remember this kind of pattern? This was from about 10 years ago or so. It was very common. You would go sign up for a new app like Yelp, and then you would give it your, it would say like, hey, let's see if any of your friends are already using Yelp. It would ask you for your email address and the password for your email, which, yeah, you're all laughing because like we now know that this is a terrible idea, right? Like, why would you let some random application log into your email account? But it wasn't just Yelp. It was everybody doing this, including Facebook. And they actually only shut this down like a couple of months ago. And this was definitely like a bad idea to begin with, but it was also kind of the only way that it was possible to work at the beginning when companies were just starting to add APIs. And we now know that you would never go and let some random application log into your email, but people would happily do this, back in 2010 because there wasn't a lot of other options. And it's because they actually wanted the end result of what this app was promising. So they want a way for Yelp to access their contacts, but they don't really want it to access their email app. So OAuth was created to solve this exact problem, which was how do we actually let apps access data in some other API, but without giving it your password? So this pattern is all about accessing data in some other system. So it's Yelp wants access to your contacts, or Last.fm is trying to pull your listening data from Spotify, or Buffer is trying to post to your Twitter account. And that is, that was the origins of OAuth, which was always about third-party apps getting access to data in some API. Now, OAuth has been extended over time to also be used for first-party logins, so you actually do use OAuth to log into, for example, Google Contacts with Google's own OAuth server. But that's sort of just an internal implementation detail, although it turns out that it's pretty important because we can take advantage of that when we're looking for holes in these systems. At the end of an OAuth flow, the result is always just the app has an access token, and now it can go and use the access token at the API. So it's going to look like this. You're going to put it in a header, in an HTTP request, go make a request to the API. The API is going to give you some data back. That access token is called a bearer token. And a bearer token is also something that is, it has a couple of interesting properties, but I like to use this analogy of checking into a hotel. So when you go to the front desk at a hotel and you check in, the person at the front desk checks your ID, and then they give you this key card. Now, that key card is like an access token, and that key card is, you then take that to the door, and the door opens up and lets you in. Sorry, I had to look at the screen because I have the different view here. That access token, that key card is like an OAuth access token. And what I mean by that is that the door, in order for the system to work, the door doesn't actually care who you are. The door doesn't need to know your identity or your user information. It just needs to know, does this card have access to this door at this time? And that's a really important property of OAuth, is that access tokens actually can be any format and it just represents access to a resource. So I want to start with talking a little bit about how OAuth works, and then we're going to look at some examples of where things have gone horribly wrong. In OAuth, there are always these sort of 5 roles, and these roles in OAuth are conceptual, not necessarily a physical thing. So, for example, if you have like a relatively small scale API like GitHub, then GitHub is providing both an API and the OAuth server as part of the same software running on the same servers. And then your application, the application is always the thing trying to get access to that server. That application is the one that's going to be getting the access token. And then it has to be able to interact with the user through something like their device. So let's take a look at the most common OAuth flow and talk about how this works, and we're going to see where we can kind of poke some holes in this. So this starts off with the user visiting the website like yelp.com or whatever this application is that's trying to get the access token. That's the user saying, hey, I'm trying to use this application. The application then says, great, please go over to the OAuth server so that I can get access. That causes the user's browser to land at the OAuth server with a bunch of stuff in the query string that describes the request, like I'm trying to log into Yelp, it wants to access my contacts. Now, these are all things that are in this URL, which means, of course, anybody can change this, which is why the OAuth server then gets the user to log in and then asks the user if this is okay. Did you really mean to log into Yelp, and do you actually allow it to access your contacts? Assuming that they say yes, then the OAuth server will generate a one-time use temporary code and return it back to the user's browser in a redirect. The user's browser takes it back to the application and says, hey, application, I'm done logging in there. The OAuth server gave me this code, this one-time use code that you can use to go get an access token. And now behind the scenes, the app can go and exchange that temporary code for an access token. It also has to authenticate itself, so it provides its own secret that it got when it registered, and then the server returns an access token, and now we're done. The app has an access token. There's an important difference between the first half of these lines and the second half of these lines. And that is that in the first part, everything is always running through the user's browser. So what's actually trying to happen here is we're trying to get this temporary code from the server to the user's browser. Or sorry, to the application, but we do that through the user's browser. Now the bottom part, the pink lines, are the application talking directly over to the authorization server. That's the back channel. The back channel is what you're like more familiar with. It's an HTTP request. It goes over SSL. It's encrypted in transport, things like that. The blue lines and everything going through the user's browser is what we call using the front channel to send data. And that is literally using the address bar of the user's browser to move data from one system to another system. So there's a lot of obvious benefits of using the back channel, which is why it's very common in web programming. It's, we validate SSL certs so that connection, we know we're talking to the right server, that connection's encrypted, and importantly, the response can be trusted because it's, again, over SSL. I like to think of it as hand-delivering a message, right? You walk up to somebody, you give them the thing, they can see you, they can see that you're giving it to them, you can see they took it and walk away, and everything's great. It sounds very simple, but it turns out that this is a very important difference from using the front channel. Using the front channel to send data is more like throwing it over a wall and kind of hoping they catch it. And I want you to think about both sides of this wall, right? Because on the OAuth server side, the cat is trying to throw this key over to the client, can't see over the wall, so it kind of just has to hope that it's caught by the right application and that it wasn't intercepted and didn't fall on the ground. And there's no way to confirm this. On the other side of the wall, that cat is just waiting for this key to fly over the wall and sees this key, catches the key, has no idea where it came from. It could have come from anybody on the other side of the wall, not necessarily the actual OAuth server. So this turns out this front channel is an extremely weak point in the whole OAuth ecosystem because neither side can confirm that the transaction was legitimate or was complete. So why do we use the front channel at all? It turns out that it is actually really important in OAuth because it is a way that the OAuth server can actually ensure that the user did give their permission for this transaction to take place. And it wasn't just the app saying, oh yeah, this user totally said it was okay for me to access their contacts because they gave me their password, right? But it's also a way that this receiver doesn't need a publicly accessible IP address, which in the web server context is not a big deal, but if you're talking about an app running on a phone, all of a sudden that's more important because a phone does not have a public IP address that something can go push data into from a server. Okay, so that's kind of like the baseline OAuth flow. This was just to kind of set some context. I want to start getting into some of the hacks and what you can do to sort of take advantage of some of the weak points in the systems. Turns out that there are a lot of ways to hack OAuth, and they are actually very well documented. And they are documented in other RFCs because, again, the core OAuth RFC was written in 2010, and it leaves a lot of room open to interpretation and a lot of options available to you as an implementer of a server or a client. And these have been these have evolved over time, and there are new RFCs that talk about, here's a handful of things that we know are a problem, here's how to solve them. And these are all thankfully well documented, well understood by the industry. And I'm actually not going to focus on these ones because you can go read them, and these documents are actually not that bad to read because they're not written like a spec telling you what to do. They're written as a way to describe an attack and a solution to that attack. So there's some links up there to some of the sections in these various documents. That last one is actually an active working group item right now, which the group is working on and trying to publish that as a best current practice. So we're going to talk about some other things that can go wrong in OAuth. And to do this, I want to share some examples of when this has gone so wrong that it has actually turned into headlines in press. Because at that point, like, you know something bad has happened. Because it's one thing to just kind of be like, oh yeah, there was this little, redirect mix-up attack thing, and someone did a bug bounty on it and told the company, and they fixed it. Great. That's not terribly interesting to me because it just means that someone built their system wrong, and we already knew the right solution, and they just didn't do it. So we're gonna talk about some things that actually did hit tech press or even mainstream press. I'm gonna start with an old one from Twitter. So in 2013, there were a bunch of these headlines that came out, which was Twitter's API keys were leaked. Now, what does that actually mean? So it turns out that somebody went and found all the API keys for Twitter and put them on GitHub. And you could go find this. It's still out there because you can't delete things from the internet. The end result of this is basically that the way Twitter's OAuth is OAuth 1, and it requires API keys, client secrets in order to work. And they would go, their own apps used OAuth, so they would issue a client ID client secret to the official Twitter for iPhone app, put it in the App Store, people would download it, and then they would log into the Twitter app, and it's not going to prompt you for permission, right? It wouldn't make sense for the official Twitter app when you log in to say, hey, is it okay if Twitter posts tweets? No, of course it's okay because it's the Twitter app. But if you're going to use Buffer, it is very important that you, as a user, see this prompt of, is it okay if buffer posts to your Twitter account? So the end result here is basically that with this client ID and client secret, anybody could go and use these in an application and sort of impersonate that application. And it's not going to necessarily give you access to everybody's data because you still have to have a user log in. But when they log in, they think they're logging into the real Twitter app, and instead they're logging into this fake app. And that might do things like, bypass the consent screen, or maybe get around rate limits because they don't rate limit their own application, but they rate limit other applications. So it is a big deal, and but it's not like everybody's accounts were hacked immediately. The moral of the story, though, is that there isn't really a good solution to putting secrets in mobile apps. You can't do it because at the end of the day, any API key you put into a mobile app and distribute through the App Store is going to be downloaded by everybody who downloads that application, and it can always be reverse engineered and extracted. So this is the solution here is that we just don't use client secrets on mobile apps anymore. And that is documented in an extension called PKCE, or PKCE. It stands for Proof Key for Code Exchange. And this is a pretty clever solution to be able to complete an OAuth exchange without using a client secret. So I mentioned that at that first OAuth flow that we saw, the reason that it works is that when the OAuth server throws that authorization code over the wall and kind of just hopes that the right client catches it, the reason that it can be sure that the right client did catch it is because that request, when it comes back and is used to get a token, also includes the app's secret, which then means nobody can use the code if they steal it. If we can't use a secret on a phone, what do we do instead, right? So there's a slight variation to this flow, which is called PKCE, which is how we do this on a mobile phone. So it starts off the same. The user launches the app and clicks login. Since the app doesn't have its own secret, it actually says now, hang on, I'm going to generate a new one on the fly right now for this particular request. And this is going to be unique for this request. And then it says, I'm going to hash the secret. And the idea with the hash is that that's a one-way operation. So if someone can steal the hashed value, there's no way for them to reverse engineer it into the original secret, at least not in any amount of time that is reasonable. So then the app says, great, go over to the OAuth server to grant me access and take this hashed value with you. So the user then lands at the OAuth server like before, but now there's also this hashed value in that URL. They log in, approve the request, and now the code is issued back to the application. So this is the point where someone could steal this code, and if they do, even if they also stole the hashed value, it turns out that it's not going to be useful because when the app goes and exchanges that code, it has to prove that it actually started the request by including its plain text secret that it used to generate that hash. Then the server can hash the plain text, compare the hashes, and now it knows that the code was not intercepted. So this is the solution for being able to do an OAuth flow on a mobile device without using a client secret. It's also usually handled by libraries, thankfully, so you don't have to worry about actually implementing it from scratch if you use any of these native libraries that sort of package it up with it. Okay, next attack is actually only kind of related to OAuth. It's actually an attack on JSON Web Tokens. And this one also was a pretty big deal. It turns out that this one didn't make mainstream press, but it definitely made like the tech press headlines of the critical vulnerabilities in these JSON Web Token libraries. And the reason this is related to OAuth is because JSON Web Tokens are often used as access tokens for APIs, which means that if you can fake a JSON Web Token, you can often get access to an API either that you didn't have access to before, or you can impersonate somebody else or change expiration dates, things like that. So what is a JSON Web Token? It is a long string of characters, and it has a particular structure. If you look closely, you'll find 2 dots in that string of characters. Those separate this into 3 parts: the header, the payload, and the signature. If you then base64 decode, which is important to remember that it's encoded, not encrypted, this is just base64 encoded JSON data. So anybody can take a JSON Web Token and see what's inside of it, which coincidentally is also a great way to find out sort of internal implementation details of APIs, because they are putting who knows what into these tokens, and you can often see what they expect and in these requests and kind of learn about them by looking inside there. And it's not encrypted, it's just base64 encoded. The way that the token is validated, the API will receive one of these JSON Web Tokens, and then it will say, okay, cool, so here's this header, here's all the payload, here's the claims, which contains like the user ID and maybe some roles, maybe expiration date, scopes of the request, what APIs it can access. At the bottom is the signature, and the signature at the bottom is typically it's using a public-private key pair to sign it. So the OAuth server that generates this will use its private key, sign the token, and then make its public keys available on the internet so that the API endpoint can use the public key to verify the signature of the token. That's great. How does that work? Well, it turns out that in the header describes how to validate this token, including this property ALG, algorithm, which says RS256. So that's the public-private key 256 method of, of doing the cryptography. That's great. So what happened was that if your validation library was using that header to determine how to validate the token, an attacker can come in and just change the algorithm. Now, it also turns out that there was an algorithm in the spec called none, which means don't verify the signature. So if you just change the algorithm to none and then drop the signature, you can then modify anything you want in the claims, send it to the API. The API is like, okay, how am I going to validate this? Well, it looks like the algorithm is none, so we're done. Great, good job, you've authenticated. That's pretty bad. It's kind of also like an obvious bug in hindsight, because essentially, like this whole thing is untrusted data until it's been verified. And if you use untrusted data to verify it, then you aren't really verifying it. There's a more subtle attack on this too, which is that, sure, so you might say, great, we're going to prevent using the algorithm none. Hard code that into the code, disallow that completely, and now you've fixed it, right? Well, no, it turns out that there's another signature method called HS256, which is using a shared secret. And there's various reasons that you may want to do this in your API instead of using public-private key pairs. But what it means is that if you change the algorithm to HS256, which says, now please use the shared secret, well, the library already knows where to go find the public key of the server, right? So you can then also go use that public key as a shared secret, create a signature, because then you're telling the library, great, go verify this using this shared secret. And it turns out that was also very easy to do. So the moral of the story here is just because something looks complicated and like someone thought it through, that's not always true. And the header here and all of this data about the token, until you verify the signature, it is untrusted data. And you should not use that in the process of deciding how to verify the token. Just like you wouldn't use a form field on a web page that determines like how to validate the rest of the form, because it's untrusted data. So the other good news is that thankfully most JSON Web Token libraries fixed this around 2015, 2016, pretty quickly after this sort of was made public. And the fix is that in your code, the library now requires that you specify which algorithms you want to be able to use. So it's only kind of a fix, because if that code says you support both public private key and shared secret, this attack still works, because you can still trick it. But most of the time we're only ever using one method, so you just hard code that in your code and it's fine. But this is definitely something, if you notice JSON Web Tokens being sent around as cookies or access tokens, that's definitely something to take a look at. Not that I'm endorsing actually trying to attack live systems or anything. Okay, next one. This one's a little trickier. This anybody here remember these headlines? It was last year. 50 million Facebook accounts were attacked. Yeah, I'm seeing a lot of heads nodding. This was a pretty big deal. The headlines were 50 million Facebook accounts were hacked. And this actually did make mainstream press, because 50 million is a very large number, and it was actually that the attacker could actually access people's accounts without them initiating the request, which is a way worse attack than just sort of theoretically having somebody be able to impersonate an application. So what I thought was really interesting about this this hack was that because it made such mainstream news, Facebook actually put out a surprising amount of detail about the attack, way more than a company normally would when there's kind of a security breach like this. And so they had their public facing on their main press website statement about whatever went wrong, sorry, we won't do it again. But they also on their security blog published a lot of details about how this attack actually got pulled off. So I want to take a look at that and see if we can analyze it and see if we can learn anything from it. And it turns out that the really interesting thing about this was that it was 3 different bugs that Facebook had that each individually didn't seem like that big of a deal. But when you stack them, then it leads to this. So let's take a look at Facebook's own words and how they describe this. So first, they have this really cool feature called View As. Well, they've taken it down. The View As feature means that you are on your profile page, you click View As, choose somebody else, one of your friends, and you can see what your profile looks like to them, which is extremely powerful feature. I wish more companies would do that because it's a very good way to let the user verify their privacy settings are correct. There was a bug in that feature, and the bug was that normally it's supposed to turn your profile into read-only because it's somebody else is looking at your page. It incorrectly showed a video uploader, which would let you wish the person happy birthday. Okay, that's not that big of a deal, right? Because you're looking at your profile page, the video uploader appears, and what are you going to do? Like post a video to your Facebook wall? Well, you could already do that anyway, so it seems like it's just a little weird UI glitch, right? So remember that, keep that in mind, and now we'll look at the second vulnerability. Secondly, there was a new version of the video uploader that they launched, which incorrectly, in their words, generated an access token that had the permissions of the Facebook mobile app. Now, this is starting to sound a little bit weird to me, and this is starting to get into OAuth, right? Because I'm assuming that internally they've got sort of like different client IDs registered for the different components of Facebook because they're a pretty big company and they have lots of different teams working on the product, not all coordinating together. So video uploader is one app, the mobile application is the separate client ID, and somehow in this case the bug was that when the video uploader, it would go and request a new access token, and that access token had the permissions of the Facebook mobile app, which means it normally was supposed to be limited to being able to only post a video. Now it could also go and do things like everything the mobile app can do, which is literally everything on your account. But again, by itself, this isn't that big of a deal because at the end of the day, it's still, you're looking at your page. Sure, this little component gets an access token with escalated privileges, but what are you really going to do with that? You can just go get, if you wanted one of those tokens, you just go use the mobile app and get it yourself that way anyway. Okay, third. Here's where it starts getting weird. When the video uploader appeared, as part of the View As feature, the access token that it got was not for you, but for the user you were looking up. Yeah. This should never have been possible. This is not something that should have been able to be pulled off because what it sounds to me like they just sort of swapped a user ID field in the access token that was generated. But when you stack these 3 things up, the end result is that you could use the View As feature to see what your profile looks like to somebody else. You would end up with an access token belonging to that user, which had the permissions of the Facebook mobile app. So basically, you have complete access to their account. And they didn't have to do anything. So, moral of the story here, I think, is it seems like they were placing too much trust in these different components of the system and letting things sort of take shortcuts. And when you are that large and that many different teams working together, you kind of have to treat everybody as an adversary. So the same way that you would not let a third-party app just be like, hey, I need an access token for this user, and the server's like, sure, go ahead. No, you need the user to be doing an OAuth flow and approve the request so that you know they agreed to it. And so just like that for third parties, you need those kind of safeguards in place for first-party apps when your system is so big that you end up with these people doing things that they aren't coordinating with each other. So yeah, treat components of your own applications the same way as third-party applications. Don't just sort of grant extra trust just because it's your own teams. Okay, last one. This one is Google, from Google, and this was in 2017, and it was either called an OAuth phishing attack or an OAuth worm, depending on the press that would write about it. This was a Google Docs phishing email or a Gmail OAuth phishing email. Basically, it was very cleverly pulled off, and I'm not sure if it's actually been fixed. So you'll tell me what you think after we look at this. First of all, does anybody see anything wrong with this picture? Would you click the allow button? So it doesn't look super wrong at first glance, right? But what if you click the little Google Docs drop-down and then this appears? So this is starting to look a little suspicious, right? What is Google docscloud.info/g.php? That looks a little fishy. Also, who is this person? Who is this email address, right? It's the developer of the application. So what's going on here is that this developer went into the Google Developer Console, created a real OAuth client, registered it, and called it Google Docs, and then gave it the Google Docs icon in the app icon settings. Google then happily gave them a client ID, and they were able to start an OAuth flow. It turns out that you can start an OAuth flow by just visiting a URL, which means you can create a URL that initiates the OAuth flow, which will look like this. So it says client ID, and here's the scope, which is sending email and managing your contacts. Then you just have to get someone to click on this link and click allow. And there's many ways to send a URL to people, right? You can run it through Bitly and send it via a Twitter DM. You can SMS it to somebody. It doesn't matter how you get it to them. As soon as one person clicks this, now you have a real OAuth access token issued to your application, which can send email from that account and read that person's contacts. So then this attacker then used the access token to send an email from that person's account to all of their friends. And the email said, this person shared a document with you. Click here to view it. So now you get a real email. This is also not a spam email because it's being sent through the Gmail API from someone to their friends. So Gmail's not going to flag it as spam. You get an email that looks maybe a little suspicious, but it says, open this into Google Docs, which, sure, okay, great. You click it. It's also a link to real Google. It's not a link to a phishing website. It's a link to accounts.google.com. And as soon as you click that, you see this prompt. And now you're already thinking about Google Docs. So you're even more likely to click it because it's real Google. It's got an SSL cert. It didn't go through a suspicious-looking URL shortener. And as soon as you do this, it repeats. And so all it takes is one person to start this, and now it just kind of escalates. And this spiraled out of control. It happened so fast that Google actually tweeted this out in the middle of this, about 20 minutes into this. They're investigating a phishing email that appears as Google Docs, which was kind of the right statement, but not quite. And then, meanwhile, there was a Reddit thread where this was being reported and discussed, and a bunch of Google engineers were chiming in on that thread, being like, "Hey, we've escalated this internally. We're working on it." And then, sure enough, about 40 minutes later, they realized what was going on, which was that there was no real hack here. It was just that a client ID had started getting access tokens and kind of gone, viral. But it was a real OAuth for the whole time. The fix was they just disabled the client ID. And the next time somebody clicked that link, they would get this page, and then that just kind of aborted the whole thing, right? They can very easily revoke all the access tokens to that application because they were all obtained legitimately. So it was very easy to sort of just stop this in its tracks once they realized what had happened. But who knows what other information had already been leaked by that point. There's no way really to tell. And this is why I say I don't think they actually really fixed it, because they just stopped this particular instance of the attack from happening. They didn't go back and change the screen that shows what the user was about to grant permissions for, because the real problem was that screen didn't make it clear that Google Docs app was a fake application. So this gets into the idea of, it turns out that consent screen is extremely important part of OAuth and is a challenge to design in a way that is not going to result in this kind of thing, because this wasn't an attack on the protocol. It wasn't an attack on there wasn't really finding a flaw in any of the exchange of data. It was tricking people into clicking allow in a pretty convincing way. So the idea is that you want to show the user you're about to give this application access to do something with your account. Do you allow this? And you need to do that in a way that doesn't overwhelm them and also effectively describes what they're about to do. So you need to provide information that's clear and straightforward with enough detail so they know what's going on, but not so much that they just click OK to make the screen go away. So this is Google's, right? It says Slack wants to access your Google account. Well, first of all, how do I know this is the real Slack? That Slack name is blue. I can probably click it. That's kind of the problem. If you make users click something extra to verify it, it's probably going to, they're probably not going to do it. And that is where this flaw came from. The one thing that I do like about this is that Google is a very complicated API. They have hundreds of different systems internally. So describing what the app will be able to do is a challenge. And they've done a pretty good job of summarizing the scopes here. So you can see it says view and manage the files in your Google Drive, but then there's that little I next to it. And if you click on that, you get more details about that particular scope. And I feel like this is a pretty good way of doing that sort of progressive enhancement of you give the user a little bit of information just enough so they know something where if they're curious, they can find more. And that's the one thing about this I like. These screens tend to look wildly different on every OAuth server because it's very just dependent on what application is providing this API. This is Wunderlist's. I think what I like here is that they call out what the app can do and also what it can't do to sort of reinforce to the user the app will not be able to change your password or delete your account. Flickr also does that with these green check marks and the red X of this application will not be able to delete your photos, which the interesting thing here is that this is, of course, with Flickr, these are photographers putting photos they care about a lot into and storing them on Flickr. They would like to sort of remind the user that they're not going to, this application won't be able to delete that from their account. This is Spotify's, which if you look carefully, you'll see that the scopes that are being requested of track what you can listen to, and receive your account data, they're written in two different fonts and two different font sizes. So it's kind of confusing. There's also that whole wall of text legalese stuff down below for some reason. So pretty much if someone looks at the screen, they're going to click the one button that has color on it, the big green button, and just ignore it because I can't even understand what's going on here. So you can see that like getting this right is a challenge. GitHub actually has done a pretty good job of both showing the application name and icon, but also the developer of the app right on this screen. It says, this is the developer of the application, which means if someone wanted to pull off that phishing attack in GitHub, it would be a lot harder. They would have to go and make a GitHub user account that's called like support or admin or some sort of generic thing that probably GitHub has already blocked those usernames from being able to be registered. And even then, down at the bottom, you notice that it says this authorizing that will redirect to this URL, which means, again, it's also right next to that big green button. So as a user, you're clicking this button. It's, again, one more reminder that, like, this is where you're going to go afterwards. Just wanted to make sure you're aware of that. And that way, if this said docscloud.info, you would probably avoid clicking that button at that point. Facebook did something really interesting with this, which is they actually put a lot of control of this into the hands of the users. So this application is requesting my friend list and my email address, but then it says edit the info you provide. And as the user, you can go in and change what scopes are granted to that application, which is very, very cool. And it turns out this mechanism has been built into OAuth from the very beginning, but almost nobody has ever actually taken advantage of it. Facebook is one of the few. Fitbit as well took advantage of this and said, here are all the scopes. They are checkboxes. As the user, you can go in and uncheck them. So you can say, I actually don't want, I want to log into this application so it can analyze my sleep, but I don't want it to see my location history or my weight. So I think that's a pretty cool feature as well. Giving the user more control and more empowering the user really to know how their data is being used. So if you take a look at all these, like what do they all have in common? There's a couple of components to this screen that are really important to make sure that the OAuth server defines. So if you're building an OAuth server and building an authorization screen, make sure that you have at least these features. So identifying, first of all, where the user is, what service are they on, because it turns out that anybody can just get dropped into one of these without having clicked a link from a login button, because you can just SMS somebody a link to drop them into an authorization interface. Identify the service, identify the application that they're logging into, both by name, but also identify the developer, and maybe even either the URL of the app or the URL of the redirect. Show what user is logged in, because people often have multiple accounts, and you don't want someone to accidentally authorize their work Twitter account when they meant to authorize their personal Twitter account. Listing the scopes. This is, again, one of the challenges of this is copywriting, because you have to write things that are really concise but also meaningful and not completely overwhelm the user with this. And of course, there's always the allow and cancel buttons. So that is the end. I hope you learned something. I really enjoy this stuff and spend a lot of time writing about it and doing talks on it. I have a couple copies of the book that I wrote available for me with me here. So if we have a couple of minutes for questions. So if you ask a good question, it's not a statement, I will give you a book. And and yeah, thank you all very much. I'll leave this up on here while we do questions.